So what exactly is duality? Duality is a phenomena by which you can represent a KVL equation into a KCL equation very easily just by looking at the network. Basically, two networks are said to be dual of each other when the mesh equation of one is same as the node equation of the other. You know KVL and KCL equations are basically used to form equations which let us solve for the unknowns. These unknowns are important when we actually have to build a circuit on a PCB board or sometime else. Now, the duality comes into picture when you have some components like inductor which you need to replace by a capacitor. Inductor being a costly and a bulky material, you would always want to replace it by some capacitor with certain value. And duality allows you to do such changes without actually changing the equation at all. Now when you apply KVL, you get equations in the form of currents into resistance is equal to voltage. And you get so many equations into this form. And when you apply KCL, you get equations in the form of V into admittance G is equal to I. Alright. So these two are said to be dual because in duality principle, when you get such equations out of two networks, these equations are same word to word. That means you just have to replace R by G, I by V and V by I. So let us see how it is done. Alright. So this is the summary of the procedure that we are going to follow when we have to make a dual. First, we need to put a node in each loop and a node outside of the network. Alright. So basically, if there are three meshes, you will get three equations out of KVL, right? And to convert this as a KCL, you will need three nodes and one grounded node so that you can get 1, 2 and 3 separate equations for current. So basically, in these three meshes, you will put these three nodes and one node outside of the network. And you'll have to convert some of the components as given like these. Alright. So resistance is converted into an admittance. So R converts into G. The inductor L converts into the capacitance C. Capacitance C converts into inductor L, whereas the voltage source converts into the current source. And the open circuit, wherever there is open circuit, you can convert it as a short circuit. So the basic idea is to form the current driving source out of a voltage driving source. So the units also remain same. If this is 1 ohm, this will become 1 mho. If this is 1 Henry, this will become 1 farad. If this is 2 farad, this will become 2 Henry. So the basic SI system unit remains the same for both the things. Now let us go into the actual example 2.27 in the book where it is asked to find out the dual of the network. This is the original network which is drawn in black. And now we need to convert this network into its dual. Let us see how we can find this out. So first, we need to look at how many meshes are present in this network. So there are 1, 2 and 3 meshes or loops present. The first thing is to put a node in each mesh. We have put node A, node B and node C respectively in these all meshes, and one of the node is kept out of the network which is named as D. Now we are going to connect all the nodes adjacent to all the nodes and also the node outside. So basically every node will be connected to every other node through any component, and whichever component we are passing through, we are going to use the dual that we just saw in the previous slide, and we'll be keeping the unit same. Now we have this node A and node B. Let us first go from node A to B, and we have the inductor that we need to pass through. So we go from A to B. Dotted lines show the connected dual network, and the inductor is converted as a capacitor that you can see here. Also, again, A to C. If we go A to C, we need to pass from this particular capacitor, and which gives you a dual of this inductor that you can see. So A to C, we get an inductor. Then we get to A to D, and to go from A to D, we need to pass from this particular current source. Current source converts into a voltage source that we have drawn here. So all the connections from A to B, A to C and A to D are completed. Similarly, you can perform all the connections with respect to B and C. Let us quickly see. From B to C, we have this voltage source and which converts as a current source. While going from B to D, we have to pass from this 3 ohm resistance, which converts as 3 mho. Also, B to A is already covered because we have already drawn the capacitor. Now, the remaining thing is C to D. While going from C to D, we pass from 2 ohms, which converts as the admittance of 2 mhos. While going from C to D, from this particular component, which is 4 henries, we get 4 farad capacitor. Now, we have just converted or reduced down the wire length as a proper circuit in this particular diagram. So the red diagram converts as a blue diagram in the dual. So basically, as you can see, this is the C node. This whole line is nothing but a C node. Okay. This whole line is nothing but a D node that we have drawn here. This point is A node. This point is B node. And we are just putting the components which are in between all these nodes. So in nodes C and D, between C and D, we have we have 2 modes this admittance. Then we have between C and A, we have 1 henries of the inductor. We are seeing the red diagram, please remember. So this is how you have drawn all the components and you get a dual. Now what are the basic uses of this dual? While solving the problems quickly, and if you have to analyze the problem very quickly while you are solving in GATE or any other competitive exam, if you have enough practice, you can easily see the dual, and if you can solve the problem using the dual of the network. You can easily form the equations if you are comfortable with current equations, and if you are comfortable with voltage equations, you can still convert it into the voltage equations. This is the basic use of dual for analysis and actual circuit component as you may have to use in hardware. So I hope you have understood this much. I will meet you again whenever you call me back. Thank you so much.